Okay, so in this recap, we'll just review some things in Module 8. Mostly in this video, we'll talk about outlier detection in multiple linear regression. So one thing to take note of, so first we're going to talk about outliers in the predictors. So when there are multiple predictors, outliers are more difficult to detect visually because you just can't produce a multiple dimension plot. So geometrically speaking, a vector of k predictor values, right, is an outlier if it is far away from the center of the predictor values in k dimensions. So as I say, it's kind of hard to visualize. A common measure to detect outliers in the predictor space is called leverage. And observations with large leverages are usually more important in determining the regression equation. Right, so typically there's this relationship that if you have a high leverage point, if your data point has high leverage, not only is it outlying in the predictor space, but it also tends to be influential in determining the regression equation. So let's just review a few things. The hat matrix is defined in equation 1, where X is the design matrix, right? So the design matrix is basically, if you imagine, right, your spreadsheet, right, and each column represents each predictor, right? So let's say you have a 3 predictor model, right? So this column represents the values for each individual in the first predictor, second predictor. The other thing with the design matrix is that the first column is all ones because of the intercept term, right? So that's the design matrix. And if you perform this operation, you get the hat matrix. Right, so the diagonal elements of the hat matrix are the leverages for each observation. Right, so that's how we find the leverages. Now, if you think about your fitted values, they can be written in these forms. The reason why that's the case is we know that your fitted values can be written using matrices. Right, your design matrix times the vector of coefficients. And if you work this part out, we know beta hat is given by x prime x inverse x prime y, right? And if you look at this, that's your hat matrix over there, right? Because that's how we define, right? So that's why it's given by h of y. So you can kind of realize, right, that leverage, you can kind of view leverage, right, as like a weight associated with your y variable to get your fitted response. Now, some properties of leverages, so that's the definition of leverage for observation I. The leverages they're all going to be values between 0 and 1, and the sum of the leverages will always be equal to p, where p is the number of parameters you're going to fit in your model. Right, so the leverage for observation I is a measure of distance between the predictors for the ith observation and the mean of the predictor values for all n. So what's the general rule in which we'll be working with to detect outliers in the predictors? So if your leverage is greater than 2p over n, we say that indicates outlying cases, right, with regards to their predictors. Now, some other books will say 5p over n, some will say 3p over n. So this isn't like a hard and fast rule. But the reason why it's like some constant times p over n is because if the sum of the leverages is p, then the average of the residuals of the leverages, it's just going to be p over n, right? So this is basically saying it's twice the average of the leverages. So that's kind of the rationale behind why it's given as 2p over n. Okay, so that deals with leverages, right? So we use leverages to detect outliers in the predictors. What I'm going to do in the next couple of slides is just to talk about some theoretical properties associated with residuals. Right, so we say the residuals, right, are what we observe in our sample, right? It's basically the error terms in our sample, right? So, right, we basically use the residuals to estimate the true errors. Right, so let's look at a few items over here. So residuals in vector form can be written like this. The reason is, in vector form, right, we can write your residual as y minus y hat. And we've already established that y hat is h of y in the previous slide. So we can write this as I minus h times y, right? So that's how we get this. Now, since the variance covariance matrix of your response is given by sigma square I, right? So I is the identity matrix. The variance covariance matrix of your ordinary residuals takes on this form. So the reason for this is the following. If you want to work out the variance of your residuals, it's basically going to be the variance associated with that term over here. So the variance of I minus H Y. Now, I is the identity matrix, so it's a constant. H is the hat matrix, which is a function of your predictors. So your predictor values are constants, are treated as constants in regression. So this part here is a constant, right? So the variance of a constant times y is basically the constant square, right? So in matrix form, this is written like this, right? Constant square times the variance associated with your y variable, but your variance associated with the y variable is sigma square. The other thing is that this matrix I minus H is idempotent, so I minus H times I minus H is equal to I minus H. So that's kind of just the derivation of that. So that's the variance covariance matrix of your residuals. A consequence of this fact is the following: is that the variance of your residuals is just the diagonal elements of this matrix, which is going to be sigma square 1 minus HII. Right? And the covariance is the off diagonals of this matrix over here. And it's going to be negative Hij sigma square. So a couple of consequences to take note of. One is, this is basically saying the variance is not constant, right? Because HII is not a constant value. So variance is not constant. And if Hij is not 0, this is basically saying the residuals are correlated. Right, which is a little bit different from the errors, right? So we say the errors have constant variance. And are uncorrelated. So some of the features that we see that we assume for the errors actually do not quite exactly apply for residuals, right? So variance not exactly constant, and the residuals are correlated, theoretically speaking, right? So that's the key. This is what we're going over, this theory. So as I say, equation 2 implies the variance of the residuals are not exactly constant. Equation 2 also implies the following, that so the variance of your residuals, equation 2 is basically saying sigma square 1 minus HII. That observations with high leverages, so high leverage means this is close to 1. And if HII is close to 1, then the variance is close to 0. Right? So if the variance is close to 0 for your residuals, that means on average your residuals will be smaller, right? Because if the variance is close to 0, means the distance, right, from your residuals from the mean of 0 is going to be small. So this point here basically tells us that if your data points are outlined in the predictor, you expect them to have small residuals, which is maybe a little counterintuitive because you expect them to have high residuals. Equation 3 implies the residuals have some correlation. Now note the following. So this means if your sample size is a lot bigger than the number of parameters you have, then the entries in your hat matrix tend towards 0. This means the following. That means this, so we said that's the variance formula, that's equation 2. So if HII tends to 0, then this term tends towards the constant sigma square. The other thing we mentioned is the correlation between residuals, negative Hij sigma, right? If this tends towards 0, then the correlation tends towards 0. So if your sample size is a lot bigger than the number of parameters you have, then the residuals will be close to constant and close to being uncorrelated. Right, so if it's a situation where this isn't true, then you're maybe a little bit more concerned that those properties don't quite exactly hold. So given the fact that the residuals don't exactly have constant variance, so we have to make a refinement to residuals to make them more effective for detecting outlying responses. Right, so basically what we do is we measure the residual of that observation when the fitted regression is based on all the observations except that particular observation. So what we use are the externally studentized residuals given by this equation over here, right? So MSE, MSE is another notation that a lot of people use for MS residual. The subscript I means is the MS residual of the model without observation I in it. Right, so this takes into account the fact that the residuals don't have constant variance. So the externally studentized residuals should be used to detect outliers in the response, and they actually follow this T distribution over here. Right, so the way we do is kind of like a critical value approach. Right, so if your absolute value of your externally studentized residual is bigger than this value, right, based on the T distribution, then observation I is outlying in the response. So we talked about outliers in the predictors, outliers in the response. What we really are concerned with more is whether these data points are influential. So these are some different measures of influence. They basically measure the difference between either the fitted value and or the regression equation with that data point or not. Right, so if you look at Cook's distance, right, this looks at the difference between the estimated coefficients without the data point and with that data point I. Same thing with DF betas, right? The difference in the regression coefficient for coefficient J with and without I. DF fits measures the difference in the fitted values with and without that observation I in the model building process. Now, if you look at all these equations, I kind of wrote that they are equivalent formulas. In all of these situations, you kind of realize this general fact that as HII becomes bigger towards 1, then Cook's distance and DF fits become larger, right? So that's why we say that, generally speaking, if you're outlying in the predictor, then tend to be influential. The other thing I'll take note of is that Cook's distance and DF betas will measure the impact of removing that data point I in all the fitted values, whereas DF fits only measures the fitted value for that observation. So that's a slight difference in what they measure. So what do we do with influential observations? So a few things I'll mention. Influential observations usually have something interesting about them that make them stand out from the other observations. So normally I say, usually those data points are the ones that you have to investigate a little bit further. Something's up with those data points that makes them a little interesting from the rest. What I suggest doing is fit the model with and without the influential observations and see how the different models with and without those influential observations answer a question of interest, and to see if the conclusions are similar, right? So if they are similar, then the impact of those influential observations maybe not so different, not such a big impact. Occasionally an observation is influential due to an error in data entry, so that could happen. And rarely do I advocate deleting an influential data point. These observations must always be addressed. Any data deletion must always be addressed. You can't just ignore them, because as I say, usually there's something interesting about them that you have to pay close attention to them.